Hi, welcome to week 5 video. Week 5 we're doing the respiratory system. We'll be doing a lot of respiratory anatomy, respiratory physiology. Start off with a little experiment. We'll do the bromothiamyl blue experiment first. Then we'll go over some spirometry, then go into some of the more of the lecture, but also laboratory for respiratory anatomy, and then some respiratory physiology, kind of going over some of the major concepts of the physiology of the lecture notes. Okay, this will kind of be a long video this week. There's a lot of stuff to cover, but as we go through, let's start off with an experiment because this will be fun. The bromothiamyl blue experiment, basically, I'll show it here. Okay. Bromothiamyl blue, okay, is pH indicator, okay, and is basically at where it's buffered at about pH 7.4, 7.6. It's going to be blue. However, when you put it in water or some kind of liquid, it can tell the pH. And so the bromothiamyl blue, when it is less than 7 in acidic conditions, it's going to be yellow. At distilled water ought to be green at pH 7.0, and then something basic would be blue. For example, blood, pH 7.4. We're going to go over what's called the bicarbonate buffer system, the equation that is involved with bicarbonate buffer system. Okay. So what we're looking at basically is a reaction that occurs in our blood. Okay. We have in our red blood cells we have an enzyme called carbonic anhydrase, and that enzyme acts as a catalyst for this reaction. However, we're going to do this reaction actually without a catalyst, and I'll show you how to do it. But basically what happens is when you have carbon dioxide in your body, it is essentially an acid because we're 70% water, and it's going to react with water and form carbonic acid. Now that carbonic acid is a weak acid, so that weak acid is going to partially dissociate, which means some of it is going to be in this form, okay, and then some of it is going to dissociate into hydrogen ion and into its conjugate base. Now the conjugate base here, this is bicarbonate. Here hydrogen ion is going to be what gives us our pH. And so pH is inverse log of hydrogen ion, so the more hydrogen ion we have, the lower the pH is going to be. Okay? And then these we'll explain in a little bit. But basically what happens is every time you breathe in or breathe out, you're going to have more or less carbon dioxide. And instead of the carbon dioxide swinging, let's say in our lungs or in our blood, and changing the pH quite a bit, it's buffered. We have bicarbonate buffer in our blood that buffers the pH of the blood, so the blood maintains at a pH of 7.4. Okay? But without it, we would have swings in pH, and that's kind of what I'll show you in this experiment. Basically, we get rid of, our cells make carbon dioxide. Okay? It's a byproduct of metabolism. Our carbon dioxide we have to get rid of. And so as carbon dioxide builds up in the blood, okay, it would push this reaction to the right, pH would go down. When you breathe, then you're going to breathe off the CO2, and then it's going to pull it over to the left. And so, basically what happens with this reaction is, depending on how much carbon dioxide we have, we can push this thing to the right or pull it over to the left. And one of the ways that we can adjust pH of our blood is by respiration. So if we are hypoventilating, like we're not breathing as much, if we haven't, we're not breathing so well, we haven't breathed in a while, let's say, for example, we're unconscious and not breathing, what's going to happen is carbon dioxide is going to build up in our blood. And then that is going to react with the water, and then that converts over to with the carbonic anhydrase enzyme, converts to carbonic acid and hydrogen ion, and we see our pH go down. It's not uncommon for a patient, might be a trauma patient who's not been breathing for a while, to come into the operating room with a pH of 7.2, 7.0. They are really, really sick if they have a pH that low. However, you can hyperventilate And when you hyperventilate, what happens is you would breathe off too much carbon dioxide. And if you breathe off too much carbon dioxide, then you pull this reaction to the left and you have less hydrogen ions, so then your pH is going to go up. When your pH starts to go up, 7.5, 7.6, something like that, that change in pH actually changes the properties of your hemoglobin in your blood, so that your hemoglobin is going to hang on to oxygen a little bit more tightly, which is a problem because that means you're not actually giving the oxygen out to your tissues. And so your tissues actually become hypoxic even though you have plenty of oxygen. It's just that the change in pH basically causes your hemoglobin to get really, really stingy with the oxygen and not give it to the tissues. This happens when this reaction gets pulled to the left. And so I have this kind of what happens for hypoventilation, hyperventilation. So this is why if you've heard of someone who's hyperventilating, that if someone hyperventilates, they can pass out. And what happens when they're hyperventilating and passing out is you're basically pulling this reaction left and the pH is going up. So what are they supposed to do to fix this? They're supposed to breathe into a paper bag. Now, why do they breathe into a paper bag? The reason why is you're supposed to catch this carbon dioxide and bring it back into your blood and then push it back over to the right and bring that pH down. When you bring the pH down, then your hemoglobin can actually deliver the oxygen out to your tissues. And so that's basically the why you're supposed to breathe into a paper bag or something. Basically, it's just to reabsorb all the carbon dioxide to keep your pH. So it's not a air, CO2, oxygen thing. It's actually a pH thing, trying to balance this reaction a little bit better. So I have a little experiment that we can do. And so this is the bromothiamyl blue experiment. Okay, if I can tilt this down to show you what's going on. Okay. There you go. Here's what we have. Okay. Take a beaker. Actually, it probably looks better without the effort. Okay. Take the beaker. We're going to put some distilled water in. Okay. And we'll fill it like halfway up. Okay. Something like that. Okay. And then we're going to add bromothiamyl blue. Now, bromothiamyl blue is going to be your pH indicator. So hopefully this distilled water is good and it's pH 7.0. So we'll see how this works. Okay. Sometimes I need to give it a little stir. So I have a straw here. Okay. So I don't know how well your color is. Maybe I can give it a little bit more, but it is it's a nice green color here. Okay. Maybe I would put it back on there. There you go. Okay. Now we can see that this is green. Okay. So we have this water at pH 7.0, and we have our pH indicator in there. And then what I'm going to do is I'm going to, kind of like when I was a kid, I'd take the chocolate milk and I'd blow bubbles in my milk. And I go like this. And pretty quickly this turned yellow. And it turned yellow because basically I added carbon dioxide to the water, and that reacted with the water. Okay, even without the carbonic anhydrous, reacted without the water. And became carbonic acid. Then that carbonic acid partially dissociated into hydrogen ion, and that dropped the pH. And so right in here, we basically have created a weak acid here, and it's shown because we pushed the reaction to the right, and we have an acid. And it's yellow. So now, what do? Well, we can pull this reaction to the right, or to the left. So we can pull it back to the left, because we just pushed it right, and we can pull it left. What I have here is these little sticks. These are not rock candy. This is Malcosorb. Malcosorb is basically a carbon dioxide scrubber. And so what we can do is we can actually absorb the CO2. And so we'll do this. Okay. And so if you see in the notes, put here that Malcosorb is a CO2 absorber. So we're going to take the Malcasorb, and it doesn't take much, and I can just pull a lot of that carbon dioxide out. Alright, and it wants to turn green until, there we go. So, I will stir it until it turns green. There we go. Okay, so now we're back to green. Okay, and we pulled it left. Now we're back here. Now you see that very easily we changed the pH. What we need to do is we need to buffer this. So I'm going to take some bicarbonate buffer. Okay. Now, this bicarbonate buffer, I'm going to put a bunch in. Okay. I'm going to put probably about 2 milliliters or so. This is plenty to buffer this this tiny, about 25 milliliters of water. There is no way possible that I could exhaust the buffer capacity of this, what I'm going to put in here. So when I put it in here, it's going to buffer it, and it's going to bring it to pH 7.6. So you're going to see it turn blue. Okay. Or 7.4, sorry. 7.4 bicarbonate buffer. And so 7.4, nice and blue, and now it's buffered. I could try the experiment again. And it's not changing. I could do this all day. It's not going to change. And the reason why is because this buffer has an acid and a base, and the base, bicarbonate, basically can absorb all of the acid that I can put in here. And so since it absorbs all the acid, all the hydrogen ion that I put in here, it's not going to change the pH. And so you don't see changes in hydrogen ion, and you don't see changes in pH. And so this is showing what happens. And your blood is buffered with bicarbonate. So in that way, when we breathe in and out, we don't change the pH of our blood. Okay. Alright, so that's a fun experiment. We get to blow bubbles here. Alright. So now, next thing we can do, fix this. Okay, next thing, we're done with the bromothionyl blue experiment, is we can talk about spirometry. Now, spirometry has to deal with ventilation. Ventilation, we're breathing air in and out of our lungs. And basically what we're doing is we're taking our lungs, we take our diaphragm, and our diaphragm is usually dome-shaped. And then what happens is when it's dome-shaped and relaxed, that's when our lungs are empty. Okay? When it contracts, it will shorten and actually pull down. And so when the diaphragm contracts, it shortens, it pulls down. It increases the volume here. When you increase the volume, you're going to decrease the pressure. Pressure and volume are inversely proportional. And so there's a law, it's called Boyle's Law, which I'll get to in a bit. Boyle's Law, pressure and volume are inversely proportional. So we increase the pressure, we increase the volume, we decrease the pressure, and so then we have low pressure in here, and so then you have air coming in. Okay, that's our ventilation. We can measure ventilation, we can measure volumes, like how full our lungs are, by using spirometry. And so what we have is what's called a spirometer. So here's just an analog spirometer here. Okay, and it's basically what I can do is breathe through it, and then it's going to measure how much air I breathe through it. Now there are a bunch of different volumes and capacities that you can measure in your lungs, like how much air is in your lungs when you're just sitting, resting, breathing. Usually your lungs are about half full. You breathe in about a half a liter, breathe out about a half a liter. Okay? You can always, at rest, you can always breathe in more. Take a deep breath in, okay? And you can also take a deep breath out. Okay? Also, it's very impossible to completely empty all of your lungs. You couldn't get all of the 300 million alveoli, all the little air sacs, to completely close up, to get all your tubing, all the bronchioles, bronchi to completely close up. So you'd still have some residual volume. And what I basically just described is this rectangle right here. This rectangle, this is, think of your lungs like a container. And so that container's full, the container's empty. Okay. Now normally you're breathing in about a half a liter, out about half a liter. That's your tidal volume, like the tides going up and down. Right? Then you can breathe in, maximum breath in. Okay, breathe in, that's called in IRV, which is our inspiratory reserve volume. Okay. Then we can take a normal breath out, okay, and then we can breathe out more. Okay, that's an expiratory reserve volume. Okay, and then there's the residual volume or reserve volume that's in our lungs that we just can't ever get out. So what we can do is we have these volumes, these 4 volumes, and they don't overlap. Okay, but when you add volumes together, they're called capacities. And so you have an inspiratory capacity as your tidal volume plus your IRV. You have a functional residual capacity or functional reserve, and that is your ERV plus your residual volume. So it's like after your tidal volume out, normal breath out, how much air is actually in your lungs. Okay. You also have a vital capacity, which is basically how much air, like if you're going to blow out the candles on a birthday cake, how much air can you get in and how much air can you push out? So like if you can breathe in, deepest breath in, and then the deepest breath out, okay, and really empty your lungs, that's called your vital capacity. Okay? And your vital capacity is going to be, usually in females will be about 4 liters, and males will be about 5. Maybe in females like 3.5 to 4, males about 4.5 to 5, something like that. Some of it has to do with gender, some maybe with age or with height. Some of it has to do with smoking, but a lot of times with smoking it's going to be basically with smoking it's going to be if you are a heavy smoker that you've lost enough air sacs, enough alveoli that you have emphysema, that would definitely affect your vital capacity. And the last one, we can add everything up, is called your total lung capacity. Okay? The formulas are here for all of these capacities. Okay. Procedures for spirometry, we have the tidal volume, the ERV, and the VC. So we can do a tidal volume, is basically you just set it at 0, and it's a normal breath out. Okay. And that's about half a liter. Okay. And so it's tough to measure, usually we just estimate that it's about half a liter. Okay. We can do an ERV, okay, expiratory reserve. So we want to breathe out, normal breath out, hold it, and then breathe the rest out. So I reset it, breathe out, hold it. And then I emptied my lungs from there. For me, it's about 2 liters. Okay. And so that's an example of the ERV. Now, we can do a vital capacity. Okay, that's the one where you take the deepest breath in and then breathe out as much as possible. Okay, and for my lecture-based classes, I do the vital capacity challenge where the winners get rewarded, and they get rewarded if they beat me too. But it's a friendly competition. The reason why we do it is because you want the vital capacity to be larger than your ERV and your TV so that you have a negative IRV. Because IRV is usually not calculated through a spirometer, because that would be asking you to take a normal breath in and then suck through the spirometer, and that's kind of gross, so we don't want to do that. Plus, it's not going to read right. And so what you can do is just do some algebra. You can take a vital capacity, okay, and then you can subtract out a tidal volume and an ERV, and then you get your IRV. So expect that, that formula. Make sure you know that formula. So these are all measuring things that, discrete volumes here, and then also capacities as we add these together, and we can measure these. But that's just measuring how much air we can hold in our lungs. Another important thing is how much air is actually going in and out. How quickly can we empty our lungs or fill our lungs? This is an issue with people who have asthma or some kind of other obstructive airway or restrictive airway disease, where they can get a lot of, hold a lot of air, just can't get it in or out. And so there's a measurement, it's called the forced expiratory volume, which means what % of your vital capacity can you exhale in, say, FEV1 in 1 second or FEV2, 2 seconds. And usually most people can exhale at least 75% of their vital capacity within 1 second. All right. If you have asthma, say, and it's acting up, then your airway is constricted. Then you might not be able to have a very high FEV, FEV1. All right. So now, let's talk about some anatomy. Okay. Respiratory anatomy. Okay. Let's start off with the airway, and so I'll show you the clean up the spirometry. Show you the airway, and here's the airway from start to finish. So you can pause this and write all these down. Okay, and so it starts up here. I just don't have enough room. So it's the airway. This is the upper airway until we hit the glottis and then the larynx. And then we have the lower airway. It goes through the bronchi, then bronchioles, and then the alveolar structures. Okay, all right. So there's the airway. Okay, one last pause there. And let's go through it. So first thing, we start with the airway. We start in our nose. So I have split head here. Okay. And so split head, okay, let's show it here. Okay. All right. Here in the nasal cavity. So he has nostrils. Nostrils are actually cartilage skin here. The holes are the nares. So you have an external nair is the hole, and then your nostrils is actually the structure of your nose. Okay. You're going to breathe in, and there's a septum, so you'd have 2 nostrils, and then when we go in here, the next structure is called the vestibule. The vestibule is just inside the nose, okay, in this area here. Okay. On this split head right here, he's kind of missing that area, but it would be right in here. The way I would explain the vestibule in here would be, this is where you're, if you're putting those breathe right strips on the bridge of your nose, that's opening up the vestibule. When you breathe in, you're going to breathe past the meatuses, are the little slits, and the conchae are the structures here. Now, sometimes with the airway, it looks like it's wide open, but in reality, the airway is not. What's happening is you have these little slits, and the air comes over the slits like coming over a radiator, and so what it's going to do is you have all this mucous membrane with cilia, so pseudostratified ciliate columnar epithelium, and these little slits, it kind of spreads the air out, and so what happens is as it goes over the conchae can trap debris, it can warm up the air, and also to body temperature, and then it can also humidify the air because you have this mucus here and it's imparting humidity, water vapor. So it's an important job to make it warmer, wetter, and cleaner, basically, when you're breathing in through the nose. Then it's going to recollect in the holes here, okay? And probably the best way to explain it is on this guy here, okay? Behind the conchae, there's a hole on each side. There would be a hole here and then a hole here. Those holes are the internal nares. The 2 internal nares, so there's a left and right one, would enter into the one nasopharynx. And now we get into the pharynx. The pharynx, right here, is the throat. And we have the nasopharynx to here. And then from here to here, we have the oropharynx. And then from here down to about there, we have the laryngopharynx. And so what are these structures? Basically, where we have the soft palate and the uvula, this point right here, okay, is that little punching bag that comes down there, that's kind of your landmark for where the nasopharynx is versus oropharynx. The oropharynx is between the soft palate and uvula and the epiglottis. Okay? Now, the epiglottis is this cartilage right here. The epiglottis, what happens is this is elastic cartilage that bends when we swallow. And so it's sticking up like this when you're breathing, and then when you swallow, it bends and curves and touches like that and covers up the hole into the larynx. The hole into the larynx is called the glottis. And so the epiglottis is on top of the glottis. Okay? And so this area right in here, this is the laryngopharynx. And then we go into the structure here. It's called the larynx. So now let me get a new model for you. So we have some big larynxes here, models, there. And we have some small larynxes here. And I like the small one here that shows. Okay. See this hole? Okay. This hole is the glottis. Okay. This is what you need to, if you're going to intubate someone, you would put the tube in the glottis. Okay. You want to find this hole and put it here, because if you start jamming it around in here without finding the hole, the larynx is going to spasm and this whole airway is just going to close up, and that is extremely bad, especially if you would have a patient that you're putting down for anesthesia. You stop them from breathing, you paralyze them, you stop them from breathing, and then you need to put that tube in the glottis. And if you don't, and in time, then they stop breathing and you can't get it open, they're in big trouble and they could die. Okay. So that's why sometimes at that point anesthesia can be, when they're intubating, that induction can be somewhat hairy, so you got to make sure you know what you're doing. Then also, okay, we have the epiglottis. So here's the big larynx here. Okay, we have the epiglottis. So every time you swallow, this thing folds down like that and covers the glottis. Okay. All right, we have some cartilages. Okay, this is the larynx. This is the voice box. We have some cartilages. We have the thyroid cartilage, the cricoid cartilage. Okay, the epiglottis shown here. We can also pull it out here. Okay. Here's the epiglottis there. Okay, and so those are the three biggest cartilages of the larynx, and there's only one of each of them, so they're the unpaired cartilages. Smaller cartilages are the paired cartilages. Paired cartilages, left and right. There's the arytenoid cartilages. Okay, there's one here and one here. And then on top of the arytenoid cartilage, I don't know how well you can see real closely, right here, there's a little horn on top, okay, from about here to here. This little horn right there, that is the corniculate cartilage, like cornucopia or it's horn. So unicorn, one horn. This is your corniculate cartilage. So the corniculate cartilage is on top of the arytenoid cartilage. We see it here also. Okay, we can see number 4. This is the arytenoid cartilage, and then we have the corniculate cartilage on top. Okay, the other, and there's a left and right for each one. The other one that's paired is actually embedded inside, okay, which isn't visible on these here. The other pair inside there is the cuneiform cartilage, okay, in there. It's a little sliver piece, basically, on left and right side. Okay. These cartilages here, these paired cartilages, are involved with vocal folds. Okay? And we have this one where it kind of just moves the fold, so you can kind of see what's happening with the vocal folds. This one here actually shows it a little bit more anatomically correct, because what you have is 2 sets of folds. You have a fold that's more superior, and right there, it's called the vestibular fold. That's protecting this fold right here. That is the vocal fold. That's elastic, dense regular connective tissue, and so it's a vocal ligament right here. And so the vestibular fold, sometimes called the false vocal cord, and then this is the true vocal cord here, the vocal fold, is inferior. And then what happens is you have muscle attached to the cartilages here, so that when you're breathing and not talking, you're going to be breathing like this, okay? And so you can get the airway open. When you're trying to make noise, when you're talking, it closes like this, and then you pass air over these folds while they're together, and then they would vibrate as the air passes through. And then you can also adjust the pitch, okay, by more tension on here, on this length, okay, to bring the pitch up and down. Okay. So that's basically the anatomy that we have here. Inferior to that, we have the trachea, and then we go into the conduction pathway that definitely lower into the lungs. And so I'm going to get the sponge lungs here. Okay. There we have the sponge lungs. This model used to be great, but now it's starting to melt on us a little bit here. And what we see with the sponge lungs is, okay, we see the trachea, then it splits. Okay, this first split is a bronchus. We have a left and a right. The first split, those are primary bronchi. Then the second split, so there's primary bronchus would go into each lung. The second split, or the secondary bronchi, would be going into each lobe. Now the lobes of the lungs are uneven. The right one has 3 lobes, and so we can see 1, 2, 3. And then there would be 3 secondary bronchi. The left only has 2. There's one here, and then one here. That's, superior, inferior, or superior, middle, inferior. The left one is not the same as the right one, and it's a little bit smaller, plus there's this little notch right in here. Okay? That little notch is called the cardiac notch. The heart is going to be sitting right in here. So that's why they're slightly different, and they have different lobes. Okay? And then we have the next branch, we have all the tertiary bronchi. The tertiary bronchi are going to all the subunits, or what are called bronchopulmonary segments. Bronchopulmonary segments here are color-coded here. There's a good picture in your PowerPoint notes that have colored lungs like this, showing all the segments, and it's basically what I use for the online test. The lecture test would be on these models here. We were supposed to get new ones, but they haven't come in, unfortunately. So these are starting to get a little bit beat up. All right. There's the lungs with the bronchi going in. Now the bronchi just keep going in. And beyond that, we just have smaller and smaller tertiary bronchi, so all these ones. The bronchi, all the bronchi in the trachea, are covered with cartilage. Okay? And so in the trachea, there's C-shaped rings with the trachealis muscle behind it. The trachea needs the cartilage because when you have those pressure changes in the lungs, you don't want the lungs to collapse. The trachea would collapse. The trachea would definitely collapse on inhalation if this was not held open by cartilage. And so you need the cartilage to hold these all open. Once we get deeper in the lungs, we tend to have less and less cartilage, more and more connective tissue, and also smooth muscle and elastic tissue. And so then as we get deeper into the lungs, we have this kind of microscopic view here. Okay, this is a lung lobule. This right here would be the end of a tertiary bronchus. We're going into a bronchiole. And then you have the bronchioles. Okay, and the bronchioles split into terminal bronchioles. We have a terminal bronchiole going down into this lobule. And so each terminal bronchiole goes into a lobule. And then from there, we have some of the, and on the key, these were keyed up here, these smaller ones as respiratory bronchi, or respiratory bronchioles. To me, respiratory bronchioles, they're called respiratory bronchioles because they have alveoli on them, the air sacs here. And so this one here, as it's coming down, at least shows that there are a couple of these little air sacs alveoli here. Now, as we go down beyond that, we're going to lose this smooth muscle, and down deep in here, say up in here would be a little tube. Okay, that's the alveolar duct. And then from the alveolar duct, we go into this little flower right in here, this little sac. This is the alveolar sac. And then all these little, look like little mini marshmallows here. All of these mini marshmallows are all the alveoli. You have about 150 million per lung, so let's say 300 million alveoli. A normal healthy person. This gives you about 2,000, say 200 square meters of surface area, which would be about 2,000 square feet of surface area. That's like the size of a nice sized house, square footage, floor plan. And so think about all that area. That's what you have inside your lungs for gas exchange. Plus the exchange where we're going between the capillaries and the alveoli, the membrane for that is about 0.5 microns, and so it's like thinner than a white blood cell. It's thinner than a red blood cell on its side. It's very, very thin, and so this facilitates gas exchange. And so most of the gas exchange that happens here in the lungs is due to the basically passive diffusion due to its each gas's partial pressure. And so now I want to get into partial pressure and some of the respiratory physiology now. Okay. All right. So now, this is where I want to talk about. Well, I can show up here. Here's the airway one more time. Okay. So we finished up airway. We want to talk about some of the physiology. Okay. All right, physiology. We have Boyle's law that I talked about. That's pressure and volume are inversely proportional. Okay. And so that's going to help with ventilation. And then we have Dalton's law and Henry's law. Okay. Dalton's law is basically air is a mixture, okay, of gases, and each gas contributes to overall air pressure. Now, air pressure, atmospheric pressure, is at, let's say, at sea level, is about 760 millimeters of mercury. So that's air pressure. Of that 760 millimeters of mercury, the majority of that pressure is due to the pressure that nitrogen exerts, because air is mostly nitrogen. And so nitrogen will exert something like over 500 millimeters of mercury. Now I'm kind of being vague here as far as the numbers because air pressure is changing. It depends on elevation. Also, the composition of air, some of the air can be dry or wet, so you have water vapor that can also contribute to partial pressure. So we have mostly nitrogen, then the next about 21% is oxygen, and so oxygen would be the next most amount. So of that 760 millimeters of mercury, oxygen would be in the air probably about 140 millimeters of mercury when it's in your lungs. Remember, you make that air warmer and wetter, and you're not moving all that air in or out, so you still have some residual air, and so that's mixing. So if you take a nice deep breath of fresh air, by the time it gets into the lungs, with some mixing of residual air and the humidity, you're going to have PO2, partial pressure of oxygen, would be right around 100 millimeters of mercury. So we'd use that as our number. Okay? So that's Dalton's law, is basically saying each gas in a mixture is going to contribute to partial pressure. PO2, oxygen, at sea level in your lungs is about 100. However, if you're going to go up in elevation, overall air pressure is lower, and that brings the PO2 lower, and so then the partial pressure of oxygen in your lungs is even lower. It could be 85 or 90 up at altitude. Okay? And so the thing is, what is driving the exchange, okay, of oxygen and carbon dioxide is the partial pressure gradient. It's not, we don't have a pump for oxygen or carbon dioxide. We actually have to have it move passively due to its concentration gradient, or partial pressure gradient. So what happens is basically we have Henry's law, and Henry's law basically says that air, say whatever the partial pressure is in air, okay, you also have partial pressures of gas in a liquid. And the partial pressure of gas in a liquid is determined by the partial pressure that was in the air and also its solubility coefficient. Now, carbon dioxide and oxygen are both lipid soluble, so they're going to go through those membranes of the exchange, epithelium and the endothelium of the capillaries, and so we don't have to worry so much about that. It's pretty much moving because of its concentration gradient. So basically, partial pressure in the gas is determining what the partial pressure is in the liquid. And going from gas to liquid, it's going to reach equilibrium. And so that's what Henry said. And so I have a little visual aid just to show you what's going on. Okay. Here's my Diet Pepsi. Okay. Right here. All right. So I just bought this downstairs, okay, just to show you. We have partial pressure in our lungs, and whatever it is of oxygen in our lungs, that's what it's going to be in our blood. Okay, whatever it is in the blood for carbon dioxide, that's what it's going to be for carbon dioxide in the air in our lungs. And so the way that you can change it, like how do you get more oxygen in? Well, you can increase the pressure. So if you increase the overall pressure, then you're going to have, let's say if you bring the overall pressure to 1.5 atmospheres, then you could probably get 150 millimeters of mercury of oxygen, in your blood and saturate your blood that way. Or you can change the composition. You could give someone straight oxygen, that's going to mix, and you could pre-oxygenate someone. And that's often what people do, say anesthesiologists will do before surgery, is they'll say, well, if we're going to have this person stop breathing for a while, we want to pre-oxygenate them and get their blood PO2 way, way up high, 200, 250 or so, and keep them, really oxygenated. And so then that way, we have a little bit more time to get them intubated and on the ventilator. So whatever the gas is, whatever the partial pressure in the gas is, that's what it's going to be in the liquid. So here, this carbonated water, okay, we have a lot more CO2, a lot more carbon dioxide. This gas in here, this air inside the bottle, because it's not open, okay, is very high in carbon dioxide. You'd say that it has a very high PCO2. And so a high PCO2 in the pop, we have a high PCO2 in this gas here. Very low PCO2 in the atmospheric air. And so what we'll do is, if I open this up, okay, and we see air bubbles coming out, it's basically because of pressure difference and a PCO2 difference. And so when we open it up, okay, now, as we replace the air in here, the carbon dioxide is going to reach a new equilibrium, very close to what's in the atmosphere. And so what's going to happen there is eventually all the carbon dioxide here is going to come out because of diffusion. And so this is why pop goes flat. Now you can make it go flat faster if we have a larger surface area here. So if I poured it out on a plate, okay, or if I kept this moving, if I stirred it, okay, and so I could, push some of the air out and pull it back, close this up, okay, shake it up, okay, make it fizz up, okay. I don't want to explode all over my computer, so I'll just show you. You get the idea. So as it's going flat, what we're doing is we're replacing mostly with nitrogen, because that's what air mostly is in here, and then displacing the and also with oxygen, and displacing the carbon dioxide. Now, how do you stop your pop from getting flat? Well, if we have a lot of CO2 in here, what I want to do is you could take a drink, pour your drink out, and then squeeze all the air out like that, and then cap it. Now, eventually it'll open up, and you'll see air in here, but this air has the same PCO2 as what's in here, because we're going to have the gas come out, and it should be at a new equilibrium. So this might stop you from your pop from going flat. However, it doesn't stand up very well in the refrigerator, so that's your choice whether you want to do that. So basically, that's showing Henry's law. Okay. All right, so we have Henry's law. The next thing I want to show you is why PO2, why PCO2 is important. The reason why is because this is how respiration happens. Respiration, external and internal, is the movement of gas across these membranes, and the movement is passive, and it's all dependent on PO2, PCO2. And so whatever your partial pressure is of oxygen, okay, that's going to determine how saturated your hemoglobin is with oxygen. Your hemoglobin has 4 subunits. Each subunit has heme. Heme holds the iron, okay? And the heme with the iron can each bind one molecule of oxygen, 1 molecule of O2. So since we have 4 subunits, 1 molecule of hemoglobin can bind 4 O2 molecules. And so we can have one hemoglobin molecule be 100% saturated, 75, 50, 25, or 0% totally desaturated. Okay? It's all dependent on your PO2. And it's not a linear curve, so basically they've drawn hemoglobin saturation curves. Basically at what PO2, at any given PO2, what is your hemoglobin saturation? Okay? It turns out that until you get fairly low PO2, your hemoglobin is fairly well saturated. And it's shown by these curves here. Now I drew different curves here. There's a curve for pH and a curve for temperature. These lines in green that I drew, this is what hemoglobin is going to do under normal conditions. This is pH of 7.4. This is a temperature of 37, which is just centigrade body temperature. Okay, you see all the red and the blues. Okay, so this is showing 4 red dots. This is your hemoglobin holding 4 oxygens and holding 3 or 2, 1 or 0. Now it doesn't jump between them because let's say if your hemoglobin is 85% saturated, that means, well, most of them, let's say a lot of them are going to be carrying 3 and some of them are going to be carrying 4, and so then it would be 85 or 90% saturated like that. And so you can have any degree here, but what's going to happen is, depending on your PO2, you're going to be more or less saturated. Now in the lungs, PO2 is about 100. So hemoglobin is fully saturated. And then when you get to their tissues, PO2 typically is about 40 millimeters of mercury. Now, look at the graph at 40. It doesn't actually deliver all of its oxygen. Hemoglobin, under normal conditions, okay, normal temperature, normal metabolism, just resting metabolism, normal temperature, pH, is going to be fully saturated, 100%, in the arteries, from the lungs, let's say, out in the aorta, pulmonary vein, heart, aorta, your arteries, get out to the tissues, fully saturated here. Gets to the tissues, exchanges with the tissues, and then now PO2, oxygen is going to move to the tissues, and PO2 is going to be about 40. Hemoglobin is about 75% saturated. Okay. So what does that mean? It means that typically your hemoglobin is carrying 4 oxygens, okay, fully saturated, and then when it gets to the tissues, it just gives 1 out of the 4 and hangs on to 3 more of them. Okay, and hangs on to the 3 of them. So it's kind of stingy with its oxygen. Hemoglobin under normal conditions is pretty stingy, where it's going to be 100% saturated, and then when it gets to the tissues, it gives 1 off, and then it'll be 75% saturated in the venous blood. Okay. Goes back to the lungs, picks that 1 up, and goes here, drops it off. Now, why would it do this? Well, under other circumstances, okay, like if you're exercising, PO2 could go down to like 20 if you're really sucking up the oxygen and creating an anaerobic situation, oxygen debt. At that point, you see how this curve just drops right off, like off a cliff. So when you go to the tissues, you could deliver, let's say here at exercise, PO2 might be 20, and you could deliver another 2 oxygen to the tissues. And so hemoglobin is really, really stingy, but it will give up oxygen if it needs to the tissues if they're demanding it. Okay. Another thing that can change how hemoglobin behaves is temperature affects how hemoglobin behaves, pH affects how hemoglobin behaves. Okay. Changes in pH can shift these curves around. It's called a Bohr shift. Okay. And so if you're starting to hyperventilate and your pH starts to go up, 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 you see how it shifts the curve left. When it shifts the curve left, it's called a Bohr shift left. When you do that, then it's going to be more saturated at any given PO2. When you do that, that means that hemoglobin is going to be way more stingy. So if we shift left on the curve here, okay, we shift this curve to the left, we change the pH, hemoglobin is going to be a lot more stingy with the oxygen and not deliver it to the tissues. This is why you pass out if you start hyperventilating. If you're not ventilating as much, at least fortunately, you would shift it pH would go down, you'd shift it to the right. Then at least at the same PO2, you'd be giving up, let's say, 2 instead of 1. You see here at 40, that instead of 75% saturated, if the pH is low, be at 50%. This is helpful because at exercise, you may be generating more carbon dioxide, which is going to bring the pH down, and then you're also possibly generating lactic acid, and that's going to bring the temperature down too. So not breathing as much or not getting enough oxygen that you know as much as you need, or exercise will change the pH, and so you could have something like hyperventilation shifting left. Okay, so hyperventilation would shift the curve left when pH goes up. Okay, exercise and lactic acid buildup and CO2 buildup would push it to the right and deliver more oxygen to the tissues. Same thing with temperature. The numbers are flipped. It's actually low temperature shifts it to the left. Low temperature. If we shift this to the left under low, and so this is what happens. Hemoglobin changes how it reacts, and when temperature gets low, when you have hypothermia, okay, your hemoglobin gets really, really stingy with the oxygen. So what happens is then you're going to have the hemoglobin hang on to the oxygen. So when you have hypothermia, it's very serious because if you're cold, you're not delivering oxygen to the tissues. And so if you fall into a lake, or think of like the movie Titanic, where Jack's sitting there, like he's not on the, he's sitting in the water, he's getting colder, 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 he's going to pass out, which he does. He passes out because the cold made his hemoglobin really stingy with the oxygen, did not deliver the oxygen to the tissues, did not deliver the oxygen to his brain, and then he passes out. So this is why hypothermia can be real dangerous, is because not only are you cold there, but also you are not getting enough oxygen to the tissues. The other way around, if you start to get hot, if you have a fever, or if you're exercising, you're delivering more oxygen to the tissues. So if you have a fever, more oxygen to your tissues, a lot of times your metabolic rate will go up and to fight the infection, but also with exercise. Locally, with exercise, one of the byproducts of exercise is going to be heat generation. You're using your muscles, one of the byproducts is heat, and you're going to warm up your tissues. And so if you're exercising, you may build up some lactic acid and shift the curve right, and warm it up and shift the curve right as well. So that's a double shift to push it really far right to make sure that you're delivering enough oxygen to your tissues. So this is how hemoglobin behaves at differences in pH and temperature, and I'm going to want you to know, basically understand these graphs here. Okay. All right. So I think that's all I wanted to cover as far as the extra explaining that I needed to on top of the Chapter 23 PowerPoints. You saw the structures in lab, bromothiamyl blue, spirometry, respiratory anatomy. We have some respiratory physiology. I know this class online right now, we have a test this week, and so you've probably, two things: either get this out of the way and then focus on your test, or focus on your test and then do this later. Remember, you have a test, a practical, and these weekly assignments due, and so you don't want to have all of this happening on Sunday night. Okay? All right. If you have any questions before you take the test or what to study, please email me. I put on the announcements as far as what's going on. Make sure you study. The test moves through pretty quickly. You can answer all the questions fairly quickly on the test. It's just that you would want all your time to do it. So you should be able, if you study, you should be able to finish the exam without a problem. If you're needing to look up every single answer, then you would not be able to finish on time. And so basically that's what we have. And so we'll see you next week. Okay? And good luck on your test this week.